Okay, now let us look at, so for instance, if you have a perfect crystal, okay, and then what will be the theoretical shear strength of this material, okay. So if you have two layers of atoms, this is layer 1 and layer 2, two atom planes, right, and if you are applying a shear stress on the material, at tau is the shear stress that is applied, and this is the interplanar spacing, and this is interatomic spacing in that plane, which is called, which is described by B, and it will have a special name when we are discussing dislocations, okay. So when you are applying a shear stress, the top row moves relative to the bottom row, right, when you are applying shear stress. And if you would plot the stress strain or shear stress versus shear displacement, or shear strain also you can put in, then the stress strain plot looks something like that, because there is an equilibrium position A, B, C. So each atom will actually pass through these equilibrium positions, right, when you are applying shear stress. So for the sake of idealization, you can actually assume this to be a sinusoidal curve. It doesn't have to be sinusoidal, but for the sake of simplification, I am assuming it to be a sinusoidal curve, and hence I can describe this tau as a sine function as k times sine 2 pi x by b. Okay, this b is the half wave, right. So now if you are talking about small displacement for small values of x, the sine 2 pi x by b can be written as sine theta. For small values of theta, sine theta can be approximated as theta. So for small displacement I can write tau equal to k times 2 pi x by b, isn't it? And if you are applying small displacement, the material is going to deform elastically, right. So you can relate elastic shear stress to the shear strain through shear modulus, right. Like you write sigma equal to E times epsilon, you write tau equal to G times gamma. Gamma is your shear strength, right. So now you replace this tau with G times x by A, then you will be able to find out that tau, your k equal to Gb by 2 pi A, and hence you can write your, generalize your expression tau as Gb by 2 pi A sine 2 pi x by b, where the maximum shear stress is going to be G times b by 2 pi A, where b is your interatomic spacing, A is your, what is A? Interplanar spacing, okay, that is important. Alright. So if you take an FCC material with a lattice constant A0, if the lattice constant is A0, in the previous expression you have tau max is equal to Gb by 2 pi A. The reason I have chosen A0 is because there is a A here, that A actually is interplanar spacing, that is DHKL. You remember? So in FCC, if the plane that we are looking at is 111 plane, then D111 would be A0 by root 3, because A0 by square root of h square plus k square plus l square, that we have calculated in the previous class, right. So that is actually our A in the previous figure. This A is our DHKL, so A is your A0 by root 3, and then tau max equal to Gb by 2 pi A, and B can be, for an FCC crystal, interatomic spacing will be A0 by root 2, right. In FCC you can see that, right. Are you able to see that? Interatomic spacing you calculate. I am not going to show you how it is, but you have to calculate. You will be able, it is very easy to see. Then you substitute the value of B in terms of A0, A also in terms of A0. A is also written in terms of A0, right. This is A equal to A0 by root 3, B equal to A0 by root 2, and then tau max equal to Gb by 2 pi A, that is G A0 by root 2 root 3 2 pi A0. A0 gets cancelled, and then eventually you get G tau max equal to G by 5.1, right? You are getting tau max equal to G by 5.1. So that is your theoretical shear strength of the material. That is when the bond will be broken. So one atom usually is in contact with this atom, and the bond between these two guys will be broken only when it passes through that peak, right? In the previous thing, the bond between these two atoms when you are applying shear is broken once it passes through that peak, and that is the maximum shear stress that is required. That is what is called your shear strength of the material. Okay, so that is your FCC. Yeah, so right, and this is your A0, right, and this is your inter atomic spacing. What is that? This is A0 by root 2, not A0, sorry. This is your A0 by root 2, and this is A0. So this will be A0 by root 2 by 2. No? So sorry, this is B, and sorry, this is root 2 A0, sorry. I am sorry. And then this distance will be root 2 A0 by 2, that is why it is A0 by 2. Okay. So for different materials, if you would calculate this tau max by G, tau max equal to G by 5.1, iron it is 0.11, silver 0.039, gold 0.039, and so on. Okay. The tau max by G value is coming out to be this value. So if you would calculate, estimate the theoretical, it should be shear strength, not shear strength. Yeah, theoretical shear strength of copper and iron. You are given E value and G value for iron and copper. So if you have to calculate theoretical shear strength, for iron it turns out to be 13 GPa, copper it turns out to be 7.7 GPa. So theoretical, this is shear strength means bond breakage energy. But in reality, what is that shear strength values? What is the tensile strength for steel? How much? 200? 200 what? Units. 200 GPa. What is the elastic modulus of steel? Elastic modulus of steel is around the order of 200 GPa, right? Mild steel. And the yield strength of mild steel is around 200 MPa. Just because the numbers are same, units should not be the same. Huh? But here we are predicting for iron itself, iron is actually softer than steel in general. You are predicting in the order of gigapascals. The theoretical shear strength is coming out to be in the order of gigapascals. But the reality is the real materials do not have such high shear strengths. And hence, there must be a reason why real materials do not have such high strengths compared to the theoretical shear strength that we have calculated just now. Probably the reason could be defects, right? So that is what we are going to investigate in the next class, what kind of defects are responsible for this reduction in shear strength in the materials. Thank you.